Okay, we're back with our trusses. Last time we did method of joints. So that was the idea that we had a truss. This is one piece of what you might think of maybe as a bridge or something like that, but it had these special rules that made it a truss. And we're dealing with 2D planar trusses, so we're not really getting off into three-dimensional trusses or anything like that. And we had the process called method of joints, where you looked at each joint individually, and you were able to analyze each joint as a 2D concurrent force system. If you were dealing with a three-dimensional truss, one that had components in more than just a plane, then you would analyze each joint as a 3D concurrent force system. But the same approach would apply. And that was good. It helped us to solve for member forces, but sometimes method of joints is a little bit slow when you want to solve for maybe this member in the middle here. So if I wanted to solve for this one, I had this loading configuration, a pin, a roller, and a force over here, and I wanted to solve for the member force in this member. So this would be member CF, A, B, C, D, E, F, so CF. I would have to, if I was using method of joints, find my reactions, at least these reactions, solve for these two members, or well, at least this one. So we have to write a method of joints, concurrent force system here, solve for this reaction, move to this joint, and I actually need this one too, probably. So maybe those two, solve for this joint to get this force. Then I can go to this joint, I have those two and these two unknown, I can finally get to this one. So it's a long process. But there is another method called the method of sections that I could use to get to this one directly. I'd still need some of these external reactions. Sometimes you don't. Sometimes you can arrange the sections in a way that you don't need the external reactions, but in this case I would need maybe these reactions and then create a section and solve for this one directly. So we're going to talk about method of sections because it is a useful process for finding, particularly when you have members on the inside of the truss somewhere, in the interior. It's a lot faster. So if you're not trying to solve for everything, or you're not trying to solve for one of these members on the exterior part, the kind of the perimeter, then method of sections might be the way to go. So there are a couple of rules for using method of sections. And we'll talk through those right now. The first rule of method of sections is that we have to take our truss and we have to completely separate it into two sections, two separate sections. You can't have little members connecting the two sections still. They have to be completely separated. So that's our first rule. And you'll use one of these sections in your analysis and the other one you won't actually use unless you solve it. I mean, it doesn't matter which one you use. In the process of creating these two sections, you can only, and I'm going to use the word cut here. What I mean there is like you're trying to draw a Freebody diagram and you imaginary cut line through the free body or through the body to create your free body, and so that's why I'm using cut. I'll try and show you in a minute. Can only cut through, oops, put two R's in there. So that's supposed to be through three members. So and one of the members should be the member of interest. So if I'm interested in this one, I should cut through it. Let's see, let's put that down here. So in our case, if this is the one I'm interested in finding the member force, so I want to know the internal force in this member, I need to cut this truss in a way that I cut through this one and two other members and make it in the truss into two separate sections. So for instance, I couldn't cut across here and accomplish that, but I would cut through this one, but I'd also cut through 1, 2, 3, 4 others. So I'd cut through 5 members, and that violates my rule here that I can only cut through 3 of them. So I would need to cut through this way to cut through member BC, CF, and EF. That would completely separate this section from that section. I'd have 2 sections and only cut through 3 members and cut through the one I'm interested in. So CF. The 3 is important. Obviously, you can cut the truss into lots of different sections with way more pieces than 3. But the 3 is important because when I create this section, it will not be a concurrent force system. If it is a concurrent force system, then I'm just doing method of joints again. Which is fine. That may be what is best. But assuming that you are actually doing method of sections, the section you create will not be concurrent force system, not be a concurrent force system. And when you have static equilibrium in a non-concurrent force system, you have the summation of forces in x equals 0, one equation. Summation of forces in y equals 0, 2 equations. I assume we're in 2D so that we are not dealing with the 3-dimensional z direction here. But I do add summation of moments equals 0. So there's the 3 equations, and that has to do with the 3 unknowns created by the 3 members you cut through. So that's where we're getting the number 3, that the limit of members that you can cut through is from the 3 equations of equilibrium for this static portion of the truss. Generally, I need to find the external reactions first, which was also true with method of joints. It's not 100% true, but generally, find external reactions first. All right, so what that means is if this is our setup, then I need to find the reactions at this pin and the reactions at this roller before I go chopping the truss into different sections. I think we're ready to work on this one. So let's create a free body diagram. We're going to have a force in a new place here. I'm not going to make it, horizontal or vertical. I'm going to put it at an angle to show you how to deal with that. We're going to have our regular roller. It's going to roll on a horizontal surface so that the reaction will be vertical. We'll have a pin over here so that we have an X and Y reaction at the pin. So let's draw that free body diagram, put some dimensions on it, all that good stuff, and see if we can work with it. There went our page. All right. So there's our little sketch of our truss that we're dealing with. We're going to have the naming convention that we normally use, which is start in the bottom left with A and go around alphabetically. It's just an easy way to name the truss members. We had, let's get it on the picture here, sort of. We had a roller at D. I said it was rolling against a horizontal surface. So that gives us a vertical reaction. We had a pin at A. There are 2 reactions, an X and a Y. They don't have to be horizontal and vertical. They have to be perpendicular to one another. I'm going to make them horizontal and vertical and say that I have this one as R RAY, and this one as RAX. And then I've got a force at C at some angle. Let's make it 3,000 pounds. Let's make that angle, just wrote on my finger. Let's make that angle 20 degrees from horizontal. Let's make these dimensions. This one will be 3 feet. Here will be 5 feet. Here will be another 3 feet, and we'll make the height. I think last time we made it 5 feet. Let's make it 6 feet this time. Let's put that over here. Okay, didn't really draw that arrowhead very well. Didn't put a leader line for it. Technically, if you're drafting, these arrowheads have a 3-to-1 ratio. So if you're concerned with that sort of thing, this is totally an aside, but if you were drafting these, drawing these arrowheads by hand, 3-to-1 ratio for the arrowhead. Totally doesn't matter for what we're doing, but there is a standard out there for that. All right, so we have a truss. We got all our forces labeled. We didn't put a coordinate system, but it's going to be our regular X and Y. We kind of did when we did these as X and Y, or at least we implied it. There we go. Now we've got a free body diagram of our entire truss. So like I said, normally what you want to do is find your external reactions first. So it is a good idea to see if you need to find your external reactions. So to do that, imagine the cut we're going to make. We're trying to find the force in member CF. That's our goal. Find what force, is it tension, is it compression, and what's the magnitude of the force in member CF. So we need to cut through that one. And then we can cut through 2 others, but we must make 2 completely separate sections. So that kind of leaves us with this as our only option for cutting this thing. So if these are our 2 sections, we could either have section ABF over here or section CDE over here. So either one that we choose is going to have at least one of the external reactions. So for instance, if I use this section, I've got to know these 2 reactions. If I use this section, I've got to know this reaction. Now in this case, I'm going to solve for all the reactions so that we have practice doing it. But if you were in a hurry or whatever, I don't know why you'd be in a hurry, maybe on an exam. So you're in an exam and you're trying to save some time, then you only need to find the reactions that are going to be on the section that you're going to work with. I am going to work with this section, so I really only need these 2 reactions. But like I said, I'm going to solve for all of them just so we can have complete solution here. All right, in this case, RAX is not 0 because we have an X component to this 3,000 pounds, so there is something to balance it out. So let's go ahead and write summation of forces in X direction equals 0. That will say, well, let's put it up here, save a little room. RAX plus only the X component of this, so 3,000 pounds times the cosine of 20 degrees equals 0. So therefore, RAX, now when I move RAX to this other side of the equal sign, that becomes negative. So I'm actually going to put the negative over here. Negative 3,000 cosine of 20. 3,000 times cosine of 20 is 218 or 2819.1. And that negative sign means that I drew this arrow the wrong direction. It really should have been pointing to the left, which is obvious when you look at this thing. If I've got 3,000 pounds more or less pulling to the right, then RAX is the only thing that can keep the truss from moving in the right direction. So it holds it pulling back in the left direction. So I should have drawn this arrow going the other way. The negative sign is telling me that. So next time I draw that arrow, I'll draw it going to the left if I draw it. All right. We can't use forces in Y because we have two unknowns there. We could write the equation, we just couldn't solve it. So we're going to use a moment. And like I normally do, I'm going to do moments about the pin at A. So here, you don't have to at all. That's just what I'm going to do. And so I'm going to do summation of moments about A equals 0. Again, that just means that I know that this truss, Freebody diagram that I just drew, isn't rotating about A. It's also not rotating about any of these other points, right? So I could have written any moment equation I wanted. I just chose A specifically because there are two unknowns. Well, one now because I solved for RAX, but these two forces will not create moments about A. I'm going to do clockwise as positive. A lot of books and other sources will show counterclockwise positive. It doesn't matter. It's totally up to you. It does affect the signs that things will be in your equation. That's why you can't really just rely on the sign to tell you if it's tension or compression or whatever, or clockwise or counterclockwise. You need something else that signifies it's clockwise or counterclockwise. So I'm using this symbol to say that clockwise are going to have positive signs. All right, like I said, these two forces do not create moments about A. If you pin the thing at A and try to push at A in any direction, you know, any orientation, the truss, the free body, doesn't rotate about A. So if you want to write them in the equation, it'll be RAX times 0. So there's 0 distance between the line of action for RAX and point A because it intersects point A. RD, so equals RD, the reaction at D. If I am pinned at A and push up in the way I drew the arrow for RD, the truss goes around counterclockwise, so that's going to give me a negative value. It has a vertical force, or vertical line of action, so I need the horizontal distance between that line of action and point A, which is 11 feet. The 3,000 pound is different. So I have to make some choices. If I am using vectors, I can do a cross product to get a moment, but I'm not using vectors, I'm using force components. So I could do this. I could extend the line of action for this force, because you can always extend the line of action. So I could extend the line of action and find the perpendicular distance between this line of action and A, which is like right, let's see, somewhere like that. So something like that. So if I could figure out that distance, I could multiply 3,000 pounds times that distance. And we have enough geometry there, we could figure it out. I don't want to do that though. I'm going to do a, to me, simpler way, where instead of thinking of this as 3,000 pounds at 20 degrees, I'm going to think of it as an x component that equals 3,000 pounds times cosine of 20 degrees, and a y component that equals 3,000 pounds times the sine of 20 degrees. And I'm going to take those two components. It's much easier for me to figure out, well, the line of action between this force and point A, or the moment arm rather, the moment arm between this line of action here and A is 6 feet. The moment arm between this force, the y component, and point A is 8 feet. So it's much easier for me to figure out that way versus trying to figure out that distance. Both of these create clockwise moments. So if I It might be hard to tell when the X component, but it would create a clockwise moment. Clearly this one does. You're pushing down on here, it definitely creates a clockwise moment. So they both create clockwise moments. So plus, I'm doing the X component first. 3,000 pounds times cosine 20 degrees. Now, it's really easy to get mentally mixed up here and think when you're writing moment equations, you're typically multiplying two numbers together, and here you're multiplying two numbers together, and forget that this is not a moment. This is just the X component. You still need to multiply times the moment arm, so the 6 foot. So you're going to actually have three numbers multiplied together. So don't forget that when you do these force components and create moments out of them. Here's the Y component, 3,000 pounds. Hopefully we don't run out of room. 3,000 pounds times sine 20 degrees. It has a moment arm of 8 feet. We're talking about this little force and its vertical line of action. So 8 feet. And those three are the only ones creating moments about point A. So they need to balance, or else my truss really is rotating about point A, which it's not doing. So they need to balance. Let's add these up. Well, let's do each one individually. So 3,000 cosine of 20 times 6 feet. So this term is 16,914.5 foot-pounds would be the units. This term, 3,000 times sine of 20 degrees times 8 feet. 8,208.5 foot-pounds. And this one is RD times 11. I'm going to move that to the other side of the equal sign. So RD times 11 feet equals, and it becomes positive when I move it over, all of this. So all I need to do is add these, divide by 11, and I have a value for the reaction at D. So let's see, 16,914.5 plus 8,208.5 divided by 11 is 2283.9 pounds, because all these feet divide out. It came out positive, so our direction that we chose for RD was correct. It really should be pointing upwards. All right, we have RAX, we have RD, now we need RAY. We could just do summation of forces in the Y direction. So again, normally I go to my diagram to write these versus trying to plug in the numbers as I go. I write down the equation based on the diagram and then plug the numbers in. So I've got RAY plus RD minus the Y, only the Y component. So 3,000 pounds times sine 20 degrees. Those need to equal 0. So now I could plug in the 2283 for RD. So RAY, I'm going to move to the other side of the equal sign. So it'll actually become negative RAY equals 22,839, which we still have in our calculator, minus 3,000 sine of 20. Uh, 1257.8 pounds. Now, but that's negative RAY, so RAY is equal to a negative 1257.8 pounds. That negative sign means that I drew this arrow the wrong way. So I drew both of these arrows backwards from what they should be. But that's okay. It just means that I need to keep track that those are going the other way. So when I draw my section, I'll draw them going the correct orientation and not use the negative sign. Now we're ready to do method of sections. We could have been ready to do method of sections quite a while ago if we had decided to do this section and we just needed to get down to RD. and we could have gone from there. But we did the whole thing just for completeness. So now what we're going to do is we're going to cut this part off and draw this free body diagram with the correct orientation for X and Y reactions and see how we find CF. All right, put that over here. So basically we have a triangle. This is A, B, C. At A, we have AX really should be doing this. So that pin that was there, this pin is actually having to pull back against the force up here. This force is trying to pull the truss this way. The pin has to pull back the other way. That was 2,819.1 pounds. RAY actually has to pull it back down. So it might not look like it. This one's pointing straight down, or not straight down, it's pointing slightly downward. It does have a Y component, but this force is really mostly pulling that way, which is trying to lift this truss up. It doesn't have to pull down a lot, but it was 1257.8 pounds that it was needing to do. We cut through these three pieces. So I'm going to do the same thing I did with method of joints, where anytime I replace a member with the member force, I'm going to treat it like a two-force member, and I'm going to draw it in tension. The tension is totally optional. You can draw it whichever direction you want to. To me, it's just simpler to draw it in tension. So this one, if it's a two-force member, you determine the line of action for the force by drawing a line through the two pins. So it's going to be just horizontal. So this would be the force in BC. And I draw it horizontal in tension and label it FBC. This one, the line of action would be between these two pins, so it's going to be at that angle. I'm going to draw it in tension. Tension just means the arrow goes away from the body as far as when I draw the tensile arrow. That is, oh, this is not C. This is F. C was up here. And then this final one, EF, is going to be a horizontal line with the force pointing to the right. Okay, we need a couple of dimensions on here. In particular, we need, this dimension was 3 feet. This height was 6 feet. And then this force, I'm just going to put, since it's at an angle, I'm going to put the measures that it was at. It was had a base of 5, a height of 6. This hypotenuse would be 5 squared plus 6 squared. Take the square root of that answer, 7.81. In case we need to do some sine or cosine on that angle, we'll have those. And then, so we have a coordinate system. We'll make X and Y like we normally would. All right, so there's the free body diagram of just this section of the truss. It's not connected to the other part of the truss. We've replaced all the members that we cut with the force in those members. And since it's a truss, those forces are all from two force members, meaning that we don't have to draw X and Y components. We can just draw a force because in a certain line, wherever that line of action is. So the line of action is defined by the two endpoints of the member. Or not the two endpoints, the two pin points. So wherever the two pins are for that member. All right, so we got this. Now we're gonna overdo it just like we did with finding all the reactions, but I need to know the force in member CF. We could solve one equation, one of our three. Remember, we have the three equilibrium equations. They fell on the floor. Here they are. We have the three equilibrium equations that we can apply to this section. We can use one of them. It doesn't always work this way, but in many cases it does. We could write the summation of forces in the y direction, this one equation, and solve for FCF, because our other two unknowns don't have y components, so they won't go in this equation. So we'll have one equation with one unknown in it. Let's do that. We have negative here, so negative 1257.8 pounds, and then a positive FCF, but we only want the y component. That's why we drew our measures here. So the y component would be 6 over 7.81. If you're not sure how this is working, it's just the sine of theta is equal to the opposite side over the hypotenuse. And since we're thinking of theta being that little angle right in there, and the opposite side is 6, the hypotenuse is 7.81, and so we're using the definition of sine versus figuring out the angle and then plugging the angle into the calculator and taking the sine of it and getting this number again. That's all we're doing. This is a plus sign. Those two have to add to 0. They're the only two in the y direction. So therefore, FCF equals, it's going to be a positive number, so it is in tension. It's positive, and that means this arrow is drawn correctly. I drew this arrow in tension, so therefore the force is in tension. Let's see what it is. It's going to be 1257.8. Move that to the other side of the equal sign. It becomes positive, and then divide by 6 over 7.81. Oh, 781. I think that'll do it. 1637.2 is what we end up with. And remember, this is a member force, so we want to specify is it tension or compression. In my scenario, I drew it in tension. I calculated a positive number, which means I drew the arrow correctly. So this is a tensile force. Now, let's assume we were not trying to find this member force. Let's say we were trying to find this member's force, BC. And we didn't already do this. Which of these equations can we use to solve for BC in one equation without having to do simultaneous equations? Again, it doesn't always work this way. Sometimes you have to write all 3 equations and solve them simultaneously, or write 2 of them and solve them simultaneously. But in this case, if we don't know either of these two and we want to know this one, then find what's common between these. And what's common is point F. In fact, they both have F in their name. And then we can do the summation of moments about that point. And neither of these, and the x component of the pin's reaction, they all have lines of actions that intersect point F. So none of them will be in this equation. So these two, if they're unknown, won't be in this equation to worry with. So I'll only have FBC in this equation. So this equation, I'll do clockwise positive just because that's what I've been doing. So FBC times its moment arm of 6 feet. No, all of those line of action intersect F, so I don't have to worry with those. And then I've got this one going around counterclockwise, so I'll give that a minus. That one was going clockwise. I didn't even tell you that, but I guess I automatically put a plus on there. So minus 1257.8 pounds, and it has a moment arm of, the line of action is here. We want to move it over to the point F that we're doing moments about. That's 3 feet. So we can solve this equation for FBC. So we move FBC to the other side. It becomes negative. This is negative, so the answer will be positive. and it'll be 1257.8 times 3 divided by 6, 628.9. And again, that came out positive, which means I drew, BC. I drew the arrow, the correct orientation for BC. I drew it in tension. So I've marked that that's in tension. All right, just to be totally complete, the last one, EF, if we hadn't done the calculations to solve for either of these. So we're starting from scratch again, and we want to find FEF, the force in this bottom member down here. We do the same thing. Well, not literally the same thing. We do the same idea. We find what these two have in common, which in this case is point C, which is interesting because we took that part away. It's not part of our free body diagram, but we know that this piece, this section of the truss isn't, rotating about point C anywhere. Even though point C is not part of our free body diagram, we know that the free body is not rotating about point C, so we can write moments about point C. I'm gonna get close to the bottom of the page. We'll try and fit it in. Should have started higher up there. Summation of moments about point C equals 0. Clockwise is positive. So at point C, both of these, their line of action intersect C, so neither of those two unknowns, we're pretending we didn't just solve for them. Neither of these two unknowns will enter into this equation. We have EF going around that's counterclockwise, isn't it? Counterclockwise. So minus EF, it has a moment arm of 6 feet. We have minus the 1257, and it has a moment arm of, well, here's the line of action. We got to move it all the way over here, 3. This distance, I don't have it labeled, but we can go back to our original drawing, and it was 5 feet. So 3 plus 5 is 8. And then this one, the X component at A, it's going to go around clockwise, so it'll be a plus 2819.1 pounds, and it has a moment arm of 6 feet. Okay, so we got to see if we can calculate all these things and figure out what EF should equal. So 1257.8 times 8, this is a negative 10,062.4 foot-pounds. This one, 2819.1 times 6 feet, is a positive 16,914.6 feet. This is just FEF times 6. I'm going to move this to the other side of the equal sign so it becomes positive. So FEF times 6 feet. We need to add these together. This is going to be a positive force, or a positive term rather. And we'll be able to solve for EF being a positive number, I think. Let's make sure we did all this right. That's negative. That one's positive. That one's also negative. Negative, positive. All right, I think we got it all set up. So 16,000 minus 10,062.4. So this sum is 6,852. We divide it by 6. We get 1142. This was a net positive. This is already positive. So therefore, FEF, the force in member EF, equals 1142.0 pounds. It came out positive, which would mean that would be a tensile force. That's weird that they're all in tension. I wonder if I did a sign wrong somewhere. It's not impossible that they're all in tension. It's just odd to me that they all came out in tension. I don't see any that we wrote backwards anywhere. I just want to check to make sure. So That's a positive, and that's negative. And this was moments about F, so that would be clockwise for BC and counterclockwise, so that looks right. And then we just checked through that one. So I think those are all right. I mean, it's just odd that they're all positive. And so it doesn't always work that you can find one of these equations to solve directly for the thing you're looking for, but many times it does work that way, where one of these equations can eliminate the other two unknowns, because you can only have 3 unknowns on method of sections. And many times it is possible to find one equation to solve for one of these. If not, then you solve for, you use multiple of the equations to either solve them simultaneously or solve them in a series chain of equations to solve for what you're looking for. Okay, last time we also talked about the idea that it's possible to calculate a member through either method of joints or method of sections, and the number you calculate comes out to be 0. And so there are members that under certain loading conditions will have a 0 force in them when you calculate them. So there are 0 force members. It doesn't mean that they are useless in the truss. It just means under that particular loading situation, where all your supports and your external loads, however you've got them arranged, in that particular configuration, in an ideal world where things don't deform and bend and all that, that those members have 0 force in them. And you can find them just by looking at the truss. So for instance, let's follow a set of rules. I guess they're rules. I'll call them rules on how to find 0 force members in a truss, at least in a 2D truss. So number one thing, you're looking for a joint with only 3 members connected to it. So in our truss, we've got joint B has 3 members connected, 1, 2, and 3, and joint E has 3 members, 1, 2, 3. This one has 2, 2. This one has 4 and 4. So only B and E in our truss here. Then you look at that joint, and you want 2 of the 3 members, I guess we'll be specific, of the 3 members to be collinear. So in other words, they share, I'll write that out. They share the same line of action. So here at B, our 3 members, there's not a set of them, 2 of them, that share the same line of action. So nothing going on here. But here at E, these 2 have the same line of action. So DE and EF are collinear. So this one is still qualifying with our rules. So the last thing is no external force. So we're not talking about internal member forces or anything. We're talking about external forces applied to the truss. So no external forces applied directly to, I'm going to put directly in here, this joint. So no external force applied at E. So that's true for us. Even if, like, we took this force and pointed it directly at E, it's not applied here, it's just pointing to it. If we did this, okay, yeah, now there's an external force applied to joint E, so it doesn't work anymore. But as long as the force is not applied to E, then if all of these are true, then the third member, or the one that's not collinear, we'll put that, the non-collinear, is a zero force member. So in our case, this one, member CE, is a zero force member. So technically you could take it out of the truss and nothing would happen, but in the real world things would happen. So for instance, if we did take this out, now this is how you would model it on paper or in an ideal setting, is that it's not there. And in fact, now that it's not there, I have a joint here that has 3 members. Now, no, it doesn't have 2 collinear, plus it's got an external force applied there, so I didn't find any new zero force members. But it is possible, and I'll draw one in a second, that there's kind of a chain reaction of zero force members being found. But without this here, the instant that these two are not collinear, so they're not collinear anymore, now they don't qualify as step 2 up here. They're not collinear. So this member is not like it's completely useless, but under the exact loading conditions and in an ideal setting where everything remains perfectly rigid, then they do calculate to be zero force. But as soon as you move the force down, you move the force, or things begin to become non-collinear, then they actually do carry a force in them. We're just talking in an ideal setting where everything stays rigid and nothing bends or anything like that. It's relatively easy to see. If we took the Freebody diagram of this joint E and we draw the tensile, like we were doing method of joints, it doesn't matter unless there's 0. It doesn't matter what their magnitudes are. When I write summation of forces in the y direction, I get, this was CE, I get that, well, FCE has to equal 0 because it's the only one in the y direction. And it doesn't matter that they're in any particular orientation. They could be arranged this way, and it would still be a zero force member. For the same reason, more or less, I could orient my axis this way if I wanted to, and I could write, well, the summation of forces in this y direction equals 0 because it's in equilibrium, and then I have some angle, FCE times the sine of that angle equals 0 because it's the only thing that has a y component. So unless theta is 0, which then basically it's collinear with these others, FCE has to equal 0. So you can prove it just with the calculations also, but it's really handy if you can look at the truss and say, oh, that's a zero force member, that's a zero force member, because it's going to speed up not having to write these equations. Plus, the other thing that it does is, let's look at this one. If I write this forces in the x direction, then let's say this was DE and this was EF. It says that FDE equals FEF. So it gives them the same magnitude, opposite directions, but same, they're both in tension, and it gives them the same magnitude. So in other words, if you find a zero force member, then suddenly you know that these two members, these two, have the same force and they're the same sense. So they're both tension or they're both compression. So now I could do method of joints here and solve for this, this, and I would know that's 0. So I could get 4 different things with just the method of joints at D over here, and identifying that as a zero force member. One other thing that can find zero force members with a different set of rules. I don't even know if I'll write them down, but here they are. I got to move this though. So let's say you have truss like this, you know, it's supported over here and got a force up there. If you ever have a joint with two members and no force at that joint, both of these are zero force members. And you can kind of intuitively tell that, you know, no matter what I do with this force or put forces all over here, if I don't put a force here, then these two, other than supporting their own weight, they're not doing anything. They're not helping the truss out. I could completely take them out and the truss would perform the same. All they're doing is adding their weight to the truss. So if you ever have two that come to a point, unless they are like collinear, if they're collinear, then, you know, they might not be zero then. Depends on what's happening on the other end. But if you have two that come to a point, unless you put a force directly at that point, then they are zero force members. If you do put a force over there, now you've got a concurrent force system that you can solve, and they have whatever your normal forces would be for something like that. So that's another type of way to find zero force members. Two members at a point with no external force at that point, both of them are zero force. All right. Two other things. One more truss thing and one more thing that's not related to trusses. All right. So this one I don't have a model of, so we just have to draw it. There's going to be a pin. We have a roller over here. And we put a bunch of bracing inside this thing. And we're going to hang some sign off of it, I guess. So we're going to put a sign here and here. Might as well put one here too. All right. So we got some forces over here hanging this sign down. So you can already see that I've got two members at a point with no force applied here, so both of those are two force members. Let's go ahead and put a force over there so that those, I mean zero force members, I said two force. These would have been both zero force members, but let's put a force over there so that that's not true. So we look for joints that have three members. So here, 1, 2, 3, 4, 4, 4, 4, 4, 3. So those two, here and here, whatever number letters those end up having. We look for collinear members at those circle joints. None are collinear here. These are collinear. So this and this are collinear. No external force applied here. This is a zero force member. So I might go in and write a 0 on top of it. If I had my little thing, I'd actually take it out. But once I do that, now I've got a new joint that has three members because this one's not here anymore. So I've got 1, 2, 3, two collinear, no external force applied at this joint. So this is a zero force member. Okay. Now I've got a joint here that has three members because I've taken that one out. So 1, 2, 3, two collinear, but I do have an external force applied here. So if this force wasn't here, then yes, this one would be a zero force member. If these forces were gone, all of these would be zero force members inside this truss. So you can set off kind of this chain reaction for finding zero force members once you find one. You know, pretend or erase or whatever to remove that one from the truss and then look again and you might find more zero force members. Okay, the other thing, last thing that I wanted to talk about is a statics topic that we haven't covered. And it's in the course. It's not a very heavy topic in the course, but it is in there, and I wanted to cover it. And it has to do with pulleys. So I guess you could have a pulley connected to a truss in some sense if you wanted to, but that's not the point of what we want to do right here. What I want to do is just these are frictionless pulleys. And just want to show you how to deal with them really quick. let's see if I can get it on the screen. Pulley system. So let's just draw up a system of pulleys similar to one that we have a homework problem on. So something like this. Let's put a pulley over here, relatively big one, and then let's do a smaller one here, smaller one. Forgot what size I made that big one. Looks like it was that size. Big one. All right, so these two we're going to connect together with some, you know, bar or whatever, and these two will connect together. This one will mount on the ceiling. This one off to the side, we'll mount it to the ceiling also. And then we're going to run a rope or a cable or whatever all the way around this pulley system. But it's going to be a single rope. It's not going to be multiple ropes. So a single rope. And let's see if we can get it around here. I'm going to draw it green just so it kind of shows up better. Now I notice I put these kind of off to the side. So that's going to affect our calculations here a little bit. But the rope comes around the pulley, goes down here, then it goes around this pulley, goes around here and comes down something like this, comes around this pulley, goes around here, comes down and ties off something like that. So we've got this one continuous rope that goes around all of our pulleys. And we're applying a force over here, and we're lifting something over here. Not the same force, so this will be a weight that we're lifting or whatever. See if I can get it kind of straight. There we go. Now, if I had drawn this more carefully, these lines would all be parallel. So let's just mark that all of these, not this one, but all of these are parallel. Even though the way I drew it, this is clearly crooked, that one's kind of crooked. If you just imagine moving this pulley in some, then they're all kind of more or less parallel. So as long as these are frictionless pulleys, then the tension in the rope does not change as it goes around the pulleys. So I'm going to say it's constant. The tension in the rope is constant. If the pulleys have tension, if there's tension between the rope and the sheave here that the pulley or that the rope is riding on the pulley, then that's not true, and that's more like what would happen in the real world. But you know, we're assuming that this is all frictionless. So this force here in the rope is the same force everywhere in this rope. So how you deal with this, if you want to find, maybe we know this force here is 600 pounds. Or, well, I wrote, it'll be fine. 500 would have been a simpler number, but 600 pounds is what I wrote. So what you do is you identify a free body diagram you want to draw. In this case, I would say that's the free body diagram. And then we draw this free body diagram. I'll do it over here. And we have our big pulley and our little pulley. I don't remember the exact sizes I chose, but something like that. And something like, I don't know, that one. And we connected them together. And then we have this 600-pound force that we're lifting. Maybe there's a hook or something attached there and we're lifting that 600 pounds. And then we cut through all these ropes. One way to draw free body diagrams is literally to you know, I usually just draw a line through something, like a line through there, but draw a circle all the way around it, and that will show you all the things that you had to cut through to replace those things with forces on your diagram. So I would have, and I'm going to draw them parallel now. This, there's one going to the center here, one coming off of there, and one coming off this side. So all of these ropes, 1, 2, 3, 4, 5, had to get cut through. They all have the same force in the rope. Ropes can only handle tension, so they all have to be drawn as tensile arrows. And then I've got a really simple free body diagram. I just write the summation of forces in the y direction equals 0. I have 1, 2, 3, 4, 5 times F, which is the force in the rope, minus 600 pounds equals 0. Therefore, F equals 600 divided by 5 pounds. 120 pounds in the rope. So anywhere in this rope, there are 120 pounds of tension, no matter where I bother to cut it, because it's frictionless around all the pulleys, and it doesn't matter what angle really is happening here. Now, if these really were at some angle, if this was a significant angle over here, then this one, when I write the summation forces in y, I'd have to take into account that angle. That's why I'm just saying that they're really all supposed to be parallel and vertical to make this even simpler. But if they weren't, if this was at an angle, then the only thing that changes is you have to do the y components of any that are at angles. Over here, this one's at an angle, you know, some angle theta. But I'm not dealing with that one. That's why in this case it might be clearer to draw a whole circle around your body, and that's not in the circle at all. It's over there somewhere. Just wanted to go over a little sample of how to deal with a frictionless pulley system, because it is a statics topic, not directly related to trusses, but I didn't have a better place to put it. So, and it's not enough to do, you know, a whole lecture on by itself. So we'll just put it here at the end of this. Okay, I think we are probably done with trusses. Outside of any kind of like example problems we need to work or things like that. We will come back to trusses occasionally, but not for any new material, just as an example problem or whatever. Okay, I will see you on Wednesday, and Wednesday we'll talk about a topic called centroids. And I think that if you're looking for the exam, if you're actually taking the class for an exam, then centroids will be the last topic on exam 1.